All right, I think it's time to get started. Welcome back. It's nice to be here with you all on a Tuesday. Oh, get out of there. Sorry, I got a pin. Pin. All right. I think we're good now. Okay, so just a reminder, we do have homework due tomorrow. I hope you've had a chance to check it out, and we're going to have our quiz on Friday. Back on that. Anybody have questions about the homework? Nope. All right. Great. Let's continue talking about grammars then. That's what we started last time, talking about grammars. This is another way to build languages. They are, I suppose, more like regular expressions than like machines, but they look like this. This is an example of a grammar. The whole grammar is called G. These S and T, and then we have these arrows. The arrows are called productions, and they describe sort of rules for substitutions. So in this example, we can make strings like, for example, if I start with the S, I'm going to use this sort of double arrow when I'm doing a particular example. I can say, the first line here, this bar here means or, so the S can become ASB, or the S can become a T. So maybe I'll do S goes to ASB. And then you can keep on doing more substitutions. Maybe I'll do that same one again, and I get AASBB. How about I'll do it one more time? AAASBBB. And then maybe I'll send the S, make the S become a T. So this now becomes that. And then the T, what can you do with the T? The T can become CT, or the T can become the empty string, epsilon. And maybe I'll do T becomes CT. And how about I'll do that same one once more? AAACCBBB. And then, sorry, there should still be a T in there. And then finally, I will make the T become epsilon. So it becomes AAACCBBB, right? The T became epsilon. Epsilon, of course, is not actually a letter in the alphabet. It just means nothing. So you could write the epsilon in there if you want to, or you could just write it like I did. This is A cubed C squared B cubed, all right? Now, I made specific choices there, but, you know, you could have done different things at every step and created a different string as your final answer. All right, this, what I just wrote, that sequence of steps, is referred to as a derivation. That's the terminology. This was a derivation of this string, A cubed C squared B cubed. All right, and the language of the grammar is all possible strings that you can get from the grammar, all possible strings that you can derive. And can you tell me like a format? I want to try and write this as a set. Anybody want to say? Can you write it in the set former notations? Yeah. A to the N, C to the M, B to the N. I like that. Where N and M can be any natural numbers. Yeah, great. Are you sure the number of A's has to be the same as the number of B's? I think you are. How do you know that? It's because you'll notice in this grammar, the only way you can create an A is if you simultaneously create a B. That means when you're through, the number of A's has to be the same as the number of B's. All right. This is a nice example of a grammar which gives you a non-regular language, which means that grammars can give you languages that are impossible to get by regular expressions. For instance, this language. You cannot generate this language using a regular expression. All right. Any basic questions? We did similar examples last time. Grammars. We're going to talk for the next few times about grammars. What kinds of languages can you express with grammars? and so on. So one thing is, some non-regular languages can be written with grammars. A natural question that actually we're going to talk about today, what if it's regular? Can all the regular languages be made on a grammar? If so, that means grammars are like strictly better than NFAs and DFAs. But maybe there are some things that you can do with the NFA, but you can't do with the grammar. We'll see. Anyway, this is where we're going for the next few times. I wanted to just do one more example. Grammars actually can be pretty weird. Grammars are allowed to be quite weird, I will say. This won't look all that weird, but I think when we start to try and think about it, you'll see this is going to be pretty weird. Let's say S goes to ASB or epsilon. This, if we take this just by itself, the language you get is A to the n, B to the n, because you can do this one step over and over again and create a bunch of A's. You will simultaneously create the same bunch of B's. All right, but you can also add steps like this. All right, this is a weird example. We are usually not going to talk about grammars that do this. Oh no, I did it again. Oh, it's okay. I'm going to turn on my rotation lock. The last time I did that during class, it was messed up for the rest of the time. Okay. Please. And my kid's school now goes till 3. So that means that the other Juliana will not be texting me during class anymore. You can text me if you want. No, don't text me. Okay. So the moral of this example here is the left side of those arrows can be actually any strings on the left side there. All right. And this can lead to some very weird kinds of languages. So, like, for example, in this case, without that second line, the language is just A to the n, B to the n. But if we include that second line, now we can derive some other strings, something like A, B, A, B. You can actually make A, B, A, B with this grammar. How would we do it? Well, you have to start with S. And I suppose the first step must be S goes to ASB. The only other thing you can do is S goes to epsilon, but then you'd be done, and I don't want to be done yet, so I'm going to go S goes to ASB. Anyone want to suggest what I should do next for the purpose of producing this string, AB, AB? What should we do next? Jeff?
AS goes to SA.
Yeah, I'm going to do AS goes to SA. Your only options really are S goes to ASB again, or AS goes to SA. In order to get AB, AB, I'm going to have to do S goes to SA. So now it says SAB, right? I substituted this AS, became this SA. And now we do that first step again. So I go ASB, AB, S becomes ASB, and now S goes to the empty string, and I end up with AB, AB. All right? So that's how we can get A, B, A, B. What is the language this time? The language of this grammar? I didn't give it a name, but basically we're going to call every grammar G, unless there's some reason to call it something else. What's the language of G in this case? Actually, I would say the language of G in this example is pretty difficult to describe. It's not obvious to me what the language is. Anybody feel like you have a good handle on what it is? I would say it includes A to the n, B to the n. Certainly, you could make anything from A to the n, B to the n. But if you additionally use this second production here, you can kind of move stuff around. I mean, you can also make this A, B, A, B, right? Which is not of that format. Anybody feel like you can describe? Maybe not. Can I just say plus more? I'm tempted to say maybe you can get any string which just has the same number of A's and B's, but you can shuffle them around however you like, although that is also not true. For instance, you cannot make BA in this grammar because you will notice when you create A's and B's, the A always has to come before the B, and by doing this step, there's no way to move a B in front of an A. So the language is something like, well, I don't know. It's hard to say. I'm just trying to, this is a weird example. I'm just trying to convince you how weird this is. Even, I mean, it doesn't look all that weird. It's not difficult to write this down, but it actually, the behavior of that grammar is not very easy to understand, right? Okay, great. Anyway, most of our examples are not going to be so weird. Let's just talk about some terminology. We've already talked about, the arrows up here are called the productions of the grammar. And then these arrows, we call this a derivation of a particular string. Some more terminology here. The alphabet letters in the context of a grammar, the alphabet letters, which we usually write them as lowercase, and usually the other ones I write as uppercase, right? So these are usually lowercase. These are called the terminal symbols in the grammar. The terminal meaning like at the end, all right? That's the sense of the word terminal I'm using here. When I look at a derivation like this, I call this is the end of the derivation, and it's over. It's really over because all the stuff here, you can't substitute any more stuff over here, all right? So those are called the terminal symbols. They're the ones that you can't make any more substitutions out of. And then the other ones, like in this example, the big S, those are called the non-terminal symbols. So the alphabet letters are called the terminal symbols, and the others, which usually I'm going to write as uppercase, just so that we can, this is not required mathematically, but it's just convenient so that you can tell at a glance which is which. The others are called the non-terminal symbols. And if there are any non-terminal symbols left in your string, it means you're not done with the derivation yet. You can still do more substitutions, all right? The terminal symbols and the non-terminal symbols. So in this example here, the terminals were A and B, and the non-terminals was S. There was only one of them, all right? And epsilon is not really either of those things. Epsilon is just sort of a visual placeholder for nothing. So it doesn't count as a symbol by itself. It represents a lack of symbols. All right. Okay, great. Let's just very briefly talk about the formal definition of a grammar. Remember we had, for NFAs and DFAs, we had the diagram of it. But the diagram really is only a visual representation of the true formal definition, which is more complicated business in terms of sets. There's a similar thing for grammars, although it's a little more straightforward actually for grammars. So formally, a grammar is a tuple. In this case, we only need 4 things in it. And we typically are going to write it this way: V, sigma, S, and P, where V is a finite set of non-terminals, like the big S and the big T in the first example we had. Those are the non-terminals. That's what the V represents. As usual, sigma is the alphabet of terminals, and it has to be finite, but it's a finite set of terminals. This is what we usually call the alphabet. S is the starting non-terminal, right? And we basically always call it S in a grammar, but it is an element of V. And this is the starting non-terminal. Sometimes just called the starting symbol. Call it whatever you like, I guess. And then P. P is the most complicated part. It is a description of what all the productions are. That's why it's called P. So P is a set of productions, and it has to be finite. So P is a finite set of productions. And each production looks like something, and then an arrow, and then something else, right? Every production has a left side and a right side, where the two things, the x and the y, can be any strings which are made up of terminals or non-terminals, or some combination of them. The only rule is the x cannot be all terminals, because it doesn't make sense. The whole point of terminals is that terminals cannot be substituted into something else. The x can be a mixture of terminals and non-terminals, but it can't be all terminals. So I'm going to say is a finite set of productions of this form where x and y are strings on V union sigma. This means the strings can be made up of non-terminals mixed together with terminals, right? V is the non-terminals, sigma is the terminals. And that's a union there. Where x, I'm going to say, contains some non-terminal. I said a moment ago, x is not allowed to be only terminals, because it doesn't make sense in a grammar to have the left side of that production be all terminals, right? And there wouldn't be terminals anymore, all right? Okay, this is the official definition of a grammar. It's more simpler than the formalized description of an NFA or DFA. So, for example, and we're not going to make it too big of a deal of this viewpoint here. If I have this grammar, which I write as S goes to AS or X, X goes to BX or epsilon. All right. This one formally, it is G equals, okay, it's the tuple. The first thing is the set of non-terminals. Someone want to shout it out? What would that be? It's the set of non-terminals. S and X, yeah. Comma. Next comes the alphabet, the set of terminals. That's A and B here. Comma. Next comes the starting symbol, or the starting non-terminal. It is S. Now, actually, when you look at the statement of G, there's technically no indication here of which is the starting, but it'll be called S basically every time. And then finally, we need the set of productions, and we're just going to write them in a list like this. S goes to AS, S goes to X, there are 4 of them. X goes to BX, X goes to empty string. And that's it. All right. So when we write the grammar, as usual, it kind of looks like there are only 2 productions here. They have this bar in them, but under the hood, those represent actually 4 separate productions. S goes to AS, S goes to X, X goes to BX, and X goes to Epsilon. All right? And, of course, if I gave you something that looks like this, it's easy enough to rewrite it in this format. Really, there's not much interesting going on here. The grammar, as we usually write it, is really not all that different from the formal description of the grammar. All right? Excellent. So let me just to continue our notational discussion here. The the various arrows that we write. So for x and y, let me say this, for strings x and y, we write x arrow y. So this big arrow here means that you can do a substitution inside of x according to one of the productions, and you obtain y as the answer. All right. So this x, the little arrow y, we write this when a single production can let us obtain y from x. All right. So when I write the x and the arrow, that means I'm doing one step of the grammar productions in a piece of x, right? X is a larger string. You're only substituting a little part of it according to one of the rules. All right. And there's another notation. We write x, the arrow star y. I haven't written this yet, but this means you can get y from x by doing several steps, or perhaps 0 steps. So the star is used in the same way that we always use the star, which is to say 0 or more times. So this means y is obtained from x by doing 0 or more productions. All right. Doing 0 means, I guess, that would only refer to situations when y equals x. All right. We can obtain y from x by doing 0 or more productions from the grammar. All right. And then just one last thing. I hope you don't mind this list of formalities here. One last thing is the language of G. This is the definition of the language of the grammar G. It is, well, how about I'll start it off. It's all strings, x and sigma star. So it's strings only made up of terminals, right? Those are what ends up in the language are only strings which are made up of terminals, such that anyone think you can translate all of this business that we set up here? What I'm going to write over here is one actually very sort of straightforward looking statement, but using the notations that I've just said up there. What does it mean that something is in the language? Yeah.
Did you say that x is in the production set?
Not quite. He said x, something like x is in P, where P is the set of productions. That's not quite right. I mean, each element of P looks like one of these things with an arrow in it. And it's not generally true. Like, for instance, in this example, AB, AB is in the language, even though this string itself, AB, AB, is not actually, doesn't actually appear as one of the production answers over here. We got another idea? I mean, the fact that AB, AB is accepted, it's really because you can write something like this, right? Is there any way we could say that? When I say something like, it is possible to write a big line with those arrows that ends up with, what do you think? I would say what I want to say here in words is we can obtain x at the end, right? You can do a bunch of stuff. Starting from, where do you start from and end up with x? Yeah, the big S, right? So what I want to write in that spot there is we can obtain x if we start with big S and do a bunch of substitutions, right? Or do a bunch of productions. Anyone see how to write that? We already have a symbol that says you can obtain this by doing several steps. Yeah.
You do the S and you do the arrow with the star in
Mm-hmm.
to the S.
Yeah, I like that. That's all it is. S derives X is one way you could read that in 0 or more steps. I mean, it won't be 0, but more steps. Right? You can start with the starting symbol S, do a bunch of steps, and end up with X. That's what it means that X is in the language. Excellent. All right, this is the definition of the language of a grammar. Now, this is just the formal definition. Usually we're not going to use the definition in this way, but it's good to know about it. Every so often we are going to want to discuss it in that sense. Any questions about that? All right. I'm going to talk for the rest of our time together about grammars and regular languages, okay? Or it's stated in another way. How can languages of grammars versus languages of NFAs. What is the relationship between these two categories of languages? All right? Languages of NFAs versus languages of grammars. So there are two questions to answer. I will just write down. Can any language of a grammar be generated by NFA? And then the sort of converse question, can any language of NFA be generated by grammar? I think one of these actually we have already answered. Anybody have an opinion about that? I think the first one actually has already been addressed by stuff that we've talked about already. If you have a language that's generated by a grammar, can you make the same language on an NFA? What do you think? No. Why not? Yeah, right. With that example at the very beginning, and we did a similar one last time, you can make a non-regular language with a grammar, right? So the answer here is no. This is because, for example, a to the n, b to the n can be generated by a grammar, but not by an NFA, because that's not regular. Not by NFA. All right, so the answer to that question is no. Not every grammar language is regular, all right? What about the second one? Can any language of an NFA be generated by a grammar? This is worth talking about. The answer here is actually yes. And we're going to talk about how to do this. So, just like in other sections, there is a procedure for converting an NFA into a grammar, all right? That's what this question is really about. So, a procedure, and it's not hard to do at all. Procedure to convert NFA to grammar. All right. Basically, each state becomes a non-terminal. So let's just do an example. It's very easy to do. It may take a moment to convince yourself that it really works. I'm inventing an NFA here. Let's put an A here, maybe an Epsilon transition over here. How about that? All right, this is an NFA. And here's the idea. Every state is a non-terminal. So in my grammar, I'm going to have the big S, the big T, and the big R are all non-terminals. And the S, being the starting state, becomes the starting non-terminal. And then each arrow or transition in the Nfa diagram gives a production. In particular, if I have something like X going to Y like this makes a production of the form X goes to AY. All right, so this is really all you need to remember in order to do this procedure. If on the Nfa you see a state X going to a state Y with the arrow A, you turn that into a production of that format. X goes to AY. All right. And accepting states. An accepting state in an Nfa signals like the end of your string, right? When you get to the accepting state, that's when you stop. So in an accepting state, if you want to translate that into your grammar, if you have an accepting state like X, this makes one more production of this format. X goes to the empty string, right? Because that's how you signal the end of a grammar production or the end of a grammar derivation, is by making your non-terminal go to the empty string. All right? If you put this all together, it's very simple to translate an Nfa diagram into a grammar. So this one right here would turn into, I have S. There's one arrow on S going to T. So that looks like S goes to AT. And that's the only thing you can do with S. And then I also have arrows dealing with T. I see T goes back to itself with a B. So I'm going to say T goes to BT. Or T can go to BR. That's because there's also an arrow from T to R labeled with a B. Or epsilon. That's because T is an accepting state. All right? Don't forget them. Accepting states always give you epsilon productions. All right? And then for R, I'm going to have a few of those, right? R has the loop edge back to itself with an A, so it looks like R goes to AR. And then I also have R goes to S with an A or with epsilon. That turns into two separate productions. That's the one with the A. How are you going to interpret R goes to S with the epsilon? How would I write that as my production here? R goes to
Epsilon S.
Yeah, you could write epsilon S, although I'm just going to write S. Right? There's no epsilon doesn't mean anything, so you might as well just write S. Right? And that's it. This is the whole grammar. All right. Maybe we should. So this is a very easy process to do. Anybody have a question about how we built the grammar? Just read each feature of the Nfa translates directly onto the grammar. Now, we should try to convince ourselves, I suppose, that you really can get the same language either way. So maybe let's look at, on the Nfa, how about the string, in this case, a string which is accepted on the Nfa would be maybe A, B, followed by epsilon, and then A, B again. So A, B is accepted on the Nfa. That means if we did this correctly, we should be able to derive that string using the grammar rules. So let's see if we can make that happen. The way to do the derivation here would be to look at how you get that thing on the Nfa and then do the same steps on the grammar. So the way you accept A, B is you start here, of course. You do A up to T, then B down to R, then the epsilon to get to S again, then A to get to T, and then the looped edge B here. This is how you accept A, B. All right, we want to try to do those same steps on the grammar. What would it look like? So in the grammar, of course I start with S. S becomes, on the Nfa, to get this string, the first thing you should do is go up to T across the A edge. So I'm going to do the corresponding production, which is S goes to AT. Next step, I go down to R, right? T goes to R with the B. So I go T goes to BR. And now it says ABR. Next step, you just have to think about what you're doing in each step on the NFA. The next step that I want to do on the NFA to do this derivation would be the epsilon transition. R goes to S. And so I do the same grammar transition. R goes to S. So here I become ABS. All right. The next step on the NFA is to do the A up to T. So I go S goes to AT. AB, AT. And then finally, I do the looped edge on the NFA. I do the looped edge. T goes to itself by a B. So I go T goes to BT in the grammar. AB, ABT. Now there's no corresponding step on the NFA, but just to finish, I make T go to the empty string. And I finally end up with AD, AB, like that. The end. All right. Any thoughts about that? Questions? This is, in my opinion, not hard to do. You just got to know how to do it and do it. I got one for you all to try. How about everybody's favorite binary arithmetic NFA? This is actually a DFA, but it doesn't matter. This is the one which accepts all strings, binary strings in binary which represent numbers divisible by 3. And this is the accepting state. All right. So your job is convert to a grammar. And then using your grammar, derive the string. I'm going to just give you a string which is accepted on the original machine, 101010. See if you can do it. Your first step should be to give the states names. I didn't give them any names, but that is part of making the grammar. You will need them to have names. I'll give you a few moments. See if you can do it. All right.
So,
Yes, I think so. Okay. All right, let's talk about these. Provided that you keep straight the process, I think it's not so difficult. So I wrote my grammar. Make sure you don't forget this this empty string here. Now, how do I derive the string using my grammar? It should go 1 0 1 0 1 0. Okay, so on the NFA, I got to go first of all 1 makes me go to t. So I'm going to go s goes to 1t. And then t, the next thing I want to see is a 0. T goes to 0r, so this will say 1 0r. Next I do the 1 at the end. It should go 1 0 1r. Next I go back to t with the 0, so it's 1 0 1 0 t. Then I do another 1 to get back to s, 1 0 1 0 1 s. And finally I do s goes to 0s, not quite finally. And then really finally, s becomes epsilon, 1 0 1 0 1 0, and that's it. All right, I hope you got something like that. This is converting an NFA into a grammar. It's easy to do, provided you remember how to do it. You'll notice in the steps of the grammar, every step is kind of the same format, right? You always have a single non-terminal on the rightmost end of the string as you go, and you are gradually building the rest of the string letter by letter on the left side, all right? This is a very kind of simple structure to this grammar here. It's because every production looks like a terminal followed by a non-terminal, right? Every production has exactly the same format except for this empty string. All right, actually there's a name for that. This grammar here, this is called, so a grammar which looks like that, this is called a single step grammar. A single step grammar. It is one in which, here's the definition. A single step grammar, G equals, V sigma S and T. A single step grammar is one in which every production looks like that up there. Every production has the form x goes to AY, or x goes to string, all right? Where x and y are non-terminals, and A is a terminal. Or possibly A is the empty string, all right? All the grammars that you could possibly get by doing that process that we just discussed, they will always look like this. They will have, all the productions have a single non-terminal on the left, and on the right side, they have a single letter followed by a non-terminal, or maybe the empty string followed by a non-terminal, or maybe just the empty string, all right? That's called a single-step grammar, and these can always be, they are the result of turning an NFA into a grammar. You end up with a single step, but actually, you can go the other way around. If you start with a single step, you can make an NFA out of it. So these, any single step grammar can be converted back into an NFA. Now, it's not true in general. You can't just start with any grammar and turn it into an NFA. But if it is single step, then you can reverse the process. So any single step grammar can be converted back to an NFA. For example, if I give you a single step, can you draw the Nfa diagram out of it? Yes, you just reverse the process that we talked about before. So here's an example. S goes to AX or BY. X goes to AX or epsilon. y goes to a s or bx or epsilon. How about that? And I'm going to try and draw an NFA from this. So let's convert to NFA. Like I said, if I give you any old grammar, you should not expect that this is even possible, because in general it's not possible to do this. But if it's a single step, then it will be possible. And we're just going to do exactly the reverse process. So first of all, I'm going to have three states called S, X, and Y, because I have three non-terminals here. So I'm going to write it like S, X, and Y. All right? And then we draw in, the starting state is S, as always. Can anyone say what among these are accepting states? Yeah, X and Y are accepting because you see these epsilons here. That's the signal that these are accepting states. Whoa, sorry about that. And then what are the arrows? Well, you fill in the arrows according to the grammar production. So S goes to AX means there's an arrow like that. S goes to BY means there's an arrow like that. All right, from X, X goes to AX means there's an arrow this way. And then for Y, it says Y goes to AS, so there's an arrow there. Y goes to BX, there's an arrow there. And that's it. This is my NFA. So these are equivalent. So any NFA can be converted to a grammar. Any single-step grammar can be converted back to an NFA. We got 2 minutes. Can I just tell you one more definition? So a slightly more capable type of grammar is not single-step, but it's called right linear. And we will talk more next time about these. A right linear grammar is one where it looks almost the same as single step. Is one where all productions have the form X goes to ZY, where Z is any string of terminals. Single step means it has to go X goes to AY, where A is a specific letter. Right linear is a little bit more general than that. The thing before the Y does not have to be a single letter. It can be any string of non-terminals. And it, of course, or this is also allowed. X goes to the empty string is also allowed in a right linear grammar. All right, so for example, here's an example of a right linear which is not single step. Something like S goes to ABAS or BAT. T goes to BS or epsilon. This is right linear. Or the word right refers to the fact that the non-terminals always go on the right side. There's also something called left linear, in which the productions, instead of looking like ZY, they look like YZ. But anyway, this is right linear, but not single step.
So is a single step grammar and right linear?
Yeah, every single step is automatically right linear. They have only one letter at a time, though. That's why it's called single step. And the right linear allows these longer strings. All right, next time we'll talk about there is a procedure to convert right linear to NFA also. It's not so hard. All right, I'll see you all tomorrow. The homework is due tomorrow. Goodbye to the folks back home. See you next time. Come on now.
Yeah, the class.